Welcome all. Today's guest is James Cormier-Chisholm from Eureka Maps Incorporated. James is a geologist by training, mine consultant. He used to work on the studies related to Voisey's Bay. James and I kind of share that common project. For the former federal government, I worked for the consulting company. James ventured into AI field 25 years ago, something like that, James?
It's almost 25 years, 24 and 3/4, I would say. Yeah.
To be precise. And along the way, developed the AI-based tool that he will present today. James, I'm going to turn it over to you, and please add a little bit more to your background, because that's pretty much everything I have.
Yeah, okay. So for basically 24 plus years, I've been working at this. It's been an effort to build it up from the ground up. There's been basically no examples before this of this sort of thing done up until the Unearth contest about 3 years ago. So in the Unearth contest, there was 2,300 international teams of data miners who competed to see who was the best. And at least on the data mining side, because it was a mixed hybrid contest with geology and data mining, I was at the top of the leaderboard on that. So I was able to test out all the work that I'd done over to that point to see how did I compare to others across the planet. And for instance, and myself and Nermina have had this conversation. One thing that I've noticed is that the Chinese have rapidly advanced in this field, so they're on top of it now, I would say. So when you look at the Chinese today, they know a lot about other countries' metal resources, more so than the countries themselves. Just I'll bring that up in the talks. So. Maybe we should just begin the talk at this point.
Yes, please. Yeah, walk us through what you learned so far and how this can be of use for the mining and especially exploration phase of the mining.
Okay.
So James, yeah, maybe you can put it in the presentation mode.
Okay, so probably, let's see if it's going to go. It's not coming up in the presentation mode on your side, right?
Not yet, but it's, I think it's quite visible, so don't worry too much about that. If you walk us through the presentation.
Okay, well, let me just, if you want, I could talk it through. I could do it that way.
Yeah, I think it's going to be more interesting if you just talk this through.
Okay, let me just get this into where it should be. Let me just shut off the video sound on this. I'd actually set this up just to play through it, so that's the problem. I just have it set up to be played through.
Yeah.
So, Nermina, it would probably be better if I just played it through.
Sure. I would say we are over prepared. We had the backup and the initial version, so trying to do both at the same time is not going to help. So while we are waiting for James, what really kind of took my attention is a statement that James is making on his I believe LinkedIn profile, where he's saying we can reduce the exploration phase from 15 or 12 or 13 or 19, whatever it is, down to 3 years using this technology. So that's considering that the duration from the discovery to the operation, average duration of development is 18 years now, maybe 16 according to other sources, where 12 to 15 years goes into the exploration. I think these tools are most definitely interesting from that point of view. The other interesting point that James is making is that it doesn't need anything but publicly available data, which will kind of really make the exploration or prospecting very interesting area for these tools. So just keep that in mind as we go forward.
Anyways, you can probably see this screen, can you?
Not really. You'll have to share the screen.
Yeah, so I'll just probably go through this for me to kill the... Can you see that screen?
No.
Let me just go back in here.
Yeah. Well, if you just flip through the presentation and through
Can
this
you see
one.
that screen?
Yes.
You can see that screen?
Yes. Yeah.
Okay, so let's just roll with that then. So, and thank you very much, Nermina, for this opportunity to present to OMOD. So let's proceed with what we have. So basically, as I mentioned, I've been doing this for 24 plus years, and I've been published in the particular area. If you look to the right, this is an article by the CIM journal, where basically in 2022, they published me on geological machine learning as applied to a Canadian situation. And if you can reference that article online, CIM, and if you plug in my name, James Cormier-Chisholm, and Eureka Maps, that article will come up as an online article that you can browse at your leisure. So what's the benefits to our approach? Eureka Maps, we can identify deposits near old mines. We can identify or potential targets for metal targets near old mines, or we can develop entirely new metal targets far away from old mines. So basically, with our technology, we can we have the same odds, if you will, of finding new deposits, whether they're near old mines or near mines. Now, our approach is a very appropriate approach for analysis of ESG concerns. So a lot of the time length that's used to develop deposits is in correlated road development when you're drilling out a new area for exploration drilling. And with our approach, with AI, we can make it a very surgical exercise of reducing that former exercise of wide area drilling down to 2% of its former area. And why do we do this? Well, the need is that industry for the past, I would say, 50 years has relied on developing new deposits around pre-existing old mines. And the reason that people have done that is that they believe the odds of the past rub off on the odds of the future. So there was work done by a man named Singer in the United States Geological Survey, who was able to determine the odds near an old mine are about 1 in 100 odds of finding a new mine near old deposits. So say, for instance, people developed the Sudbury Basin here in Canada. Everybody saw that, well, I have these same sort of odds. But what's occurred over a long period of time is that those easy to obtain odds are no longer available. And if you look at this graph here on the top, you can see that we've gone using this approach of drilling out properties near pre-existing mines. We've gone from 940 mines down to 278 mines over the last several decades. What's happened is the supply of easily to obtain targets near pre-existing mines has basically dried up. And this phenomena has expanded worldwide. So if you look at the worldwide deal flow for new properties, you'll see that on the graph below, the number of deals has steadily decreased over the last several decades due to this approach of relying on the chance of the historical chance of drilling your old mines to develop new mines. As an approach, it's no longer appropriate. With geological data mining, though, we've made a big change. So, for instance, if you look at if you go for greenfield odds, nobody wants to go towards greenfield odds. It's a 1 in 10,000 chance of finding a new mine. And this is the odds that PDAC has come up with. However, with our approach, we basically, with 50% odds, with 3 boreholes, we can change that odds. So if you look at the top here on the upper right, it's $124 million to basically find a mine in terms of drilling. So you're going to basically be drilling 6,900 boreholes to find a mine nowadays if you're doing greenfield exploration. And the reason being that when you look at geophysical targets, a lot of those geophysical targets are empty of actual metals. With our method, if you look at the middle of the chart, to obtain 50% odds, you need, like I said, 8 boreholes. So you're looking at roughly $144,000 of drilling to get that initial primary discovery. So it's a massive change with the geological machine learning. And we do have a competitor down in Australia who has done field trials, and I can see they're basically doing something very similar to what we're doing, and they're getting the same odds. The only difference being they have the exact same odds, but I think they spent about $2 million to discover a mine, as opposed to my figure of 144K. So moving on, let's give you some examples of what we've done recently with geological machine learning. So we initially tried to promote this with the Canadian government. We had a lukewarm reception by NRCan. NRCan, after several months of interaction, basically said, look, we're trying to develop our own geological machine learning map. Basically, we want a group of bureaucrats to develop this map, and we don't want industry interest in this area. So after that, I moved on to developing a complete geological machine learning map of South America, Middle America, Mexico, for instance, and America, and Africa. So we're going to give you a few examples from those particular situations. Now, Argentina itself is a very interesting situation. it has three different opportunities that I see. There's been a steady removal of government barriers to mine development down in Argentina with the new leadership there. And they've steadily improved their local geological data. And what I see in my geological machine learning maps is the place is a terrific opportunity for metals exploration. We are currently developing a client down there, a billionaire, who is getting us to look at basically 9,600 square kilometers of property area for one property. The other property is 2,400 square kilometers. Massive properties, and at height in the mountain ranges down there. And what we're seeing is what you see on the screen here, for instance. Here's a typical example that I'm seeing down in Argentina. In the yellow there that you see going through the middle of the screen, that's 50 grams per ton gold showing up in our geological machine learning maps of Argentina. And the blue, what we're looking at is about 1.5% copper, the deep solid color blue in the middle of the screen. And the dotted blue represents 300 grams per ton silver. That's a co-target, if you will, in that area. If you look to the right, those big blocks there, the big yellow block is a different type of data mining that we're applying. So we're applying two different types of data mining. One is more surface, and the other one, the bigger blocks, are gravity-based data mining, both based on geochemistry predictive targets. So that big block of yellow there represents 5.75 grams per ton gold at depth. So what we're seeing is tremendous resources in Argentina showing up in our geological machine learning maps. And it looks like a great opportunity for any exploration outfit taking a look at that area. Another example that we're going to pull up is what we pulled up basically an illegal mine out of MineDat. And typically you see these things all over the place down in South America. What they did is they pulled up a copper-rich pegmatite. So a typical scenario that most of us geologists see is where your boss says, well, okay, I want you to go and assess this area that somebody did a quick assessment on MineDat on. I want you to do a little bit of a survey in there and see what else you can find. So my suggestion is what could help you here is to buy one of our maps, because we can kind of expand on what we see in these types of situations. For instance, down there, that illegal mine was only mining gold. Well, if you see these four yellow blocks on the screen here, those are basically 5.75 gram per ton or more at depth, indicated gold metal targets, right, basically clustering around that MineDat image. However, what's not shown in that MineDat image from the previous slide is we have 3% molybdenum showing up in that area as well, which you can see in if you look to the left, there's basically a molybdenum block of resource there. So as a geologist, you can now start thinking ahead of what kind of mineralogies you would expect that weren't shown on MineDat. For instance, if you look at the lower block here, we're looking at the green dotted block. That's platinum at 20 grams per ton potential mineable target. So you're now starting to look at that and say, well, I should be expecting platinum group metals. And it starts to shape how you start to think of this area. Well, now that we know we have platinum, well, gold's pretty easy and fairly quick to assay for. Well, platinum groups, now we have to start expecting about a 3-month cycle to send all the assays off to, for instance, South Africa to do an assay on those particular mineralogies. So with the maps, you also get an idea of things that you didn't anticipate from just mine data alone. You're starting to now look at it and start to think of each of those blocks. Well, gee, I should kind of go down there with maybe a geochemistry portable rig and start to drill out the centers of those blocks, because your highest chance of intercepting a metal containing mineralogy are at the center of those blocks that I'm showing on that screen. So that then can lead to a major drilling program, because now you've taken a small diameter core, you've assayed that core, and that then leads your boss into a little bit more excitement, because now he's starting to think, well, we have something here that we can potentially mine or develop into a mineable resource. So this is just a very general example of how myself, say as a geologist, I would kind of look at these things. It kind of prepares you for the next step, if you will. Now, there are some really pretty wild deposits that we're running across in South America that are fantastic interest for copper, for instance. Now, our technology, unlike hyperspectral technology, it can punch right through overlying vegetation. So what you're seeing here is a picture or a classification picture that's basically in the depths of the deepest jungles of South America. And what we're seeing in the red is 3% copper. And what we're seeing in the blue is molybdenum at 3%. Now, I want to draw back this picture a bit. And we're going to talk about this next picture, this same area. I'm just drawing back the satellite image to give you more of an overview. So what we're looking at here basically is about 50 separate potential targets that have an aerial extent for copper. I'm just going to talk about copper alone. For 3% copper of 278 square kilometers of aerial extent of potential targets for copper. So to give you a kind of an apples to apples comparison, Escondida is 36.7% smaller in aerial extent. If I was to stretch my classifications across Escondida than what's shown up here. So basically, Escondida is the largest copper resource on the planet. And basically what I'm proposing to folks is this particular area here represents 36.7% more mineable material, at least from a superficial copper viewpoint, than Escondida. The other thing I want to point out is the molybdenum content. You see all the slightly lighter blue in the middle areas of this classification image. That's molybdenum. So there you go. There's another potential mineable resource. And then we have massive blocks of 5.75% gold running through these areas. And if you look to the right, you can see some of the blocks correspond to the copper deposits. So those are kind of a polymetallic situation, copper, gold. So you're making money not only in molybdenum, you're making money on the gold, you're making money on the copper, gold, molybdenum. So a massive resource in the middle of nowhere. And if you look hard on this image, you can see there's actually no roads into this area. So what the benefit of geological machine learning is in an area like this area could trigger a lot of rejection of the project from the perspective if we approach this like a typical project where we laid in drill roads everywhere. Probably there would be massive protests that would develop through the development of this resource. But in this case, with geological machine learning, what you want to do is drive one single road into this massive cluster of mines, and then specifically send out roads to every one of those clusters, and develop roads within those clusters to drill it out for the resource definition phase. So it's a much more efficient way to approach these sort of things from an exploration point of view. The old-fashioned way is you would lay a grid across this thing, you drill everywhere, and then you would almost inevitably, it's almost an inevitable process that you would trigger non-governmental organization protests from environmental groups if you just go and bang apart the countryside. So the next example is what I see out all the time. So yes, I can go far afield with these sort of geological machine learning maps, but we've also noticed a lot of situations of what we call resource sterilization, where you'll see, in this case, what we're looking at is basically Andes Mining Corporation came back in the 30s, and they developed this mine in Chile, and they laid out this plan that you see on the screen here. If you look on the lower right, that was the town. You look on the upper middle part, that's where the deposit was. And then they had a tailings facility to the right with a processing plant. So that's how they laid it back out in the 30s, and then it became a mine, and then they worked it over, and everybody left after a while. They thought they had used up all the resources in that area. So with resource sterilization, what they hadn't realized was, if you look on the right circled area, they'd actually put the town over 3% copper back in the day in the 1930s. So that's resource sterilization. They put infrastructure over an actual deposit, according to the geological machine learning. And if you look to the right, you can see a massive area of potential copper that they put partly most of the tailings facility through. So another obvious situation of resource sterilization in an old mining area, and more percentage copper there than the actual Andes mine, which was at 1.8%. We're looking at 3% here. So they just missed with their mine the actual higher grade copper. So I see this all the time. I see it through Canada. I see it in the US. I see it in Mexico. It happens all the time that I see these resource sterilization situations where, you know, in this case, that's an old dead town. You want to move the town. You want to you just want to demolish the town, scrape it aside, put a mine in there. So just want to point that out. Now in Canada, again, like I said, the NRCan sort of rejected my work. I gave them some very complete maps to test on. They rejected even testing the maps. I developed copper, gold, cobalt, nickel, neodymium, and graphite maps right across Canada for superficial deposits and deep gravity-based deposits. So where the deposits match, where they cross, that's your most extraordinary opportunity to find a nice vertical mine that gives you both a surface mine and an at depth mine. So you can just keep mining forever on something like that. So that's the idea of myself doing two completely different geological machine learning runs to where they match is where you find the most value. So keep that thought in your head as we go on to the next slide here. Now, this is a quite famous mine in British Columbia. And I just want to point out a very simple fact of this classification. Now, this is 10 gram per ton gold, this classification. And if you look down where the white arrow points from, that is the head frame of the mine shaft. So that head frame is connected to a vertical drop elevator, basically, that goes right down to the main deposit for this rather famous BC mine. And as you can see, those yellow classification blocks at 10 grams per ton gold are nailing the mine. But let's just pull the picture out, the same mine. I pull it, and if you look to the upper right, that's the previous picture, the existing mine. With the geological machine learning, again, I'm going to go back to that point where you have superficial classifications, which I use surface shapes to define using geological machine learning where potential deposits are, where they match with the deep gravity-based data mining for 10 gram per ton of gold, like you see on the left here. So if you look at where those little red arrows are pointing on the left, that's where you'll see sections where you'll have surface connected to the source of the gold, if you will. Those represent very, very good opportunities for deep mines that hold value over a long period of time, because you have surface down to source. So you have a connected geometry, if you will. So think about that. So up in the upper right here, to the right of this alpine glacier, famous mine, they're on the gold, but the gold's at an angle. You go to the left on the other side of the alpine glacier, that's a nice deep to surface vertical mine. It's delivering value from day one as you mine it, and it'll keep delivering value for the next several decades because both classifications match, the surface with the deep. Okay, so we're going to move on to something else that I've noticed. So here is yet another mine from BC. I seem to be picking on BC here a little bit, but bear with me. So this is a very good high-grade mine. It's been around forever, actually, and you'll see a little bit of blue in this image. I've basically have taken their 2022 43101, and I've georectified, or an image taken from their actual report, onto the actual mine. I fit it to the local stream beds and I've matched the roads around the mine so that image that you see there is an exact match superimposed from what the consultants believe is the main resource for this mine. So, and I don't want to get into who created the report because they're a rather famous consultant firm who does this all the time, 43101s, but the operation right now has, as far as I can see, and other than the 43101, I don't really have a great familiarity with the mine, but I can see that they have a current open cast mine that they're working at. And where you see this arrow here, we'll go on to this in the next slide. In that arrow is where the open cast mine is. Now, that red and yellow is 50 gram per ton of gold. And as you can see, with the current open cast mine, my company's product is basically nailing their existing open cast mine that they're working at right now. The consultant, on the other hand, all that blue bit that you see there, that's basically extracted from the report and fit onto the landforms around the mine. And I would suggest, from what I can see here, they've actually missed the main resource. It's a pretty complicated geology. Like, they actually don't have the geology still to this day nailed down. And they've been drilling this deposit since 1991, and they still don't have it quite figured out. So geology as it is, there's several geologies mixed in this area. That the geological machine learning does not have a problem with different geologies. We've trained this particular algorithm on geologies in Australia, in the USA, all of Canadian data. It's a very complete trained algorithm across basically all the geologies that I publicly could obtain for my company across the planet. So it has no problem defining where the actual ore body is here that should be looked at. For instance, that we can see that they should actually move their interest, if you will, to the southwest, or to be more sensible, and we can see in this next slide where I've zoomed in on the area where they're actually working their open cast mine. They have 1 ton mega bags in this. If you look at the circled insert image, you can see that they're actually they're basically taking their crush and they're throwing it in 1-ton mega ore bags, and they're shipping it elsewhere for processing. So I can see that in the aerial, and I can see all the extensions to their existing open cast mine. I would suggest the consultant should have just simply extended this existing mine that they were working. You can see that the great value up to the north here of where they're actually working. So with geological machine learning, you can immediately start to go, well, I really should be drilling in these patches of yellow here. These should be my more defined target areas for future drilling. Let's go back again. So otherwise, you're going to deal with this situation. You're off the gold. And when you look at that blue, only the southern portion of their understanding of where the deposit is. That's basically their understanding. Our understanding is they should be extending out this open cast mine in these areas. And to the west, there's a massive area there that's should be developed. Now it looks like it's on somebody else's property, but again, that becomes a transactional phenomena, if you will, when you see with that sort of thing. With data mining, you might want to negotiate with somebody to obtain their properties, seeing this sort of situation. The other thing we ran across is, well, the idea came from the banking industry. Originally, when I was trained in data mining, before I developed geological data mining, they had this phenomena where you could train algorithms on the holes in credit card applications and detect fraud by the information people left off the credit card application. However, with geological machine learning, it's a completely different situation, and I'm going to get into that as we go through two case examples. So here's an epic fraud. This is way back when I was working on Boise's Bay. Actually, the fraud was revealed. Basically, there was three main actors in the Bre-X scandal. There was David Walsh. Unfortunately, the gentleman died of a brain aneurysm back in the day. The main character was Michael de Guzman, who was the geologist who worked on who's the local geologist who worked on the Busang deposit in Indonesia. And he was identified as the main individual who had tampered with gold samples. I believe he started off taking shavings off his wedding ring to throw off samples, and then later he started buying river gold off of locals, and he started to add this river gold to the core boxes, and then he would crush the core, and then he would submit that in for geochemistry analysis assay. And right off the bat, of course, most people keep half a core or whatever around for people to inspect later. He didn't do that, so that immediately there was some warning bells there that nobody noticed. The other gentleman was John Felderhoff, who he's dead now, died of natural causes, but he was later a judge said that he wasn't at fault for this particular fraud. He wasn't really, he was operating more as a promoter. He wasn't really on site enough to gain an understanding of the deposit there, even though he was a geologist. So that was what came down in the court case. So massive fraud. The stock went from 30 cents to $250 per share. Was the biggest fraud in Canadian history, if you will, in the stock market. And I guess if we had what I have now 24 years ago, it would be a different story. That's my suggestion, because as we can see on this next slide, it took me several hours to find an article online where I could find the coordinates of the old Bre-X camp, but I found it in Indonesia. And this tiny little old Bre-X camp, which you can see way up way up there in the upper left-hand side, basically there's no gold there, according to my worldwide gold model. So none at all. But if you go to the right, you can see in Kampong Tahuri, this is actually, there's a town there. That's what the town of Kampong. That's obviously where Guzman was obtaining his river gold, because what you're seeing there in yellow are the data mine has identified bedrock that's gold containing at 50 grams per ton of gold. So my thinking here is that the river gold was coming from bedrock that river systems were intersecting across this area around Kampong Tahuri. So as a geologist, I kind of look at it like, well, why didn't the guy just, ask where the river gold came from and, establish, the properties over where the mineable, potential mineable area was, That would be my first thought just as a geologist, right? Just ask, right? Obviously didn't. So, and it makes sense. Actual fact, if you look at how the river works, it's hard to see on this aerial photo because it's all jungle in here. But there's a river system that connects the old Briex camp to basically Kampong. So basically, Guzman went down there, shopped a bit, spent, I believe, around $60,000 in his money to obtain some river gold, and went back up to the camp, seeded his core boxes, and crushed them so nobody could. They'd have a hard time identifying, I guess, rounded pieces of river gold, and hence we have the one of the largest scandals that ever occurred in Canadian history that actually created the process of the 43-101 report. So we didn't really have those reports before then. The second example, and it's an alleged fraud, is the red pine fraud alleged in Ontario. And as I mentioned in Eureka, this in fact is all of Red Pine's claim blocks. It's shocking actually, because it shocked me, because basically it was like these guys missed the dartboard completely here. Around this Red Pine property, there's several potential exploration targets revealed by data mining. Like it's a metal dense area for targets. But for whatever reasons, geometry, luck of the land, or whatever, they just happened to land on basically nothing for gold. So Red Pine was claiming they have an economic resource for gold. The data mine, as you can see from the middle of the screen, shows nothing, just like Briex. Now you see the purple that cuts through the upper left side of the screen and the lower right. That's 0.6% potential nickel. Now, a few years ago, that would have been exciting, but right now, at 0.6% nickel, because of what's happening with China rapidly expanding nickel supply in Indonesia, you pretty much need almost like a 1.5% nickel mine to be economic nowadays. So you can't really get excited, for now at least, for these at depth, because these are gravity-based data mining classifications that you're seeing here on the upper left and the lower right. You can't get really excited at 0.6% nickel. So this literally took me 5 minutes to check this property to see if they had anything of worth to look at here. So we trained a model for this 50 gram per ton gold model, and we have gold, copper, and nickel identified across the planet, basically. But we're going to focus on gold because it's basically gold is portable. It's money. So we're going to take a look at Saudi Arabia, because Saudi Arabia now is in the process of its conversion from an oil and gas-based economy to metal-based economy. So they're going around and promoting themselves now as a metal-based economy. So we're going to just take a very quick look here at how that looks for us. with geological machine learning. Now, if you look along where this arrow points, along the Red Sea, just south of where the Nome City project is, in the old Midian biblical area where they used to mine for copper and gold, this is where we're looking at. This is going to be our example here. But I want to just point something out about this 50 gram per ton geological machine learning. When you find deposits at this level, economically, it's a good way to filter for economics of potential mineable targets. So, for instance, if you were to find a mine at 50 grams per ton gold, according to the geological machine learning, you're basically looking at a net present value of $17.4 billion for a mine, a reasonable mine. And with an internal rate of return, I had 400% there. It actually was 399%. And if you look at what Barrick uses, their go, no-go criteria is 20% for IRR. So that's pretty exciting when you start to see these 50 gram per ton potential gold areas for exploration popping out. So if you look at the upper left here, what we have is we have the Saudi government's understanding. They've taken gold samples where every one of those yellow dots is. So this is right from their Saudi Ministry of Mining. If you look at the lower right, this is Eureka Maps worldwide 50 gram per ton gold model. And I've superimposed the government exploration for actual gold on what we see from a geological machine learning viewpoint. And with the exception of one spot to the, looks like the west there, across that highway, we can see that for the most part, if I was to approach this from a machine learning point of view, I would direct those government geologists to the north and to the east, where those nice yellow patches are, as being the most likely places to find a lot more of that 50 gram per ton gold. And where they did find the gold, I would trace that line along the coastline and sample that line for 50 gram per ton gold, because definitely a mineable situation from the perspective of a target. So you'd want to develop out that a little bit better than what the government geologists have done to date, but just to show that things do correspond with absolutely new exploration, because these results only came out this year from the Saudi government. So looking back in that area, that's a rift zone. So this previous zone slide here along the Red Sea rift zone. So we're looking at basically vein-based geological gold targets. We look here. We also have in Saudi Arabia 50 gram per ton coming out of some rare volcanoes that are emitting 50 gram per ton gold, volcanic material. So there's 3,000 volcanoes in KSA. Basically, the main takeaway from this slide is that we're not hindered by a different geology. So one was vein-based geology. This was coming out of a volcano. The data miner has been trained on such a different variety and plethora of geologies that we pretty much have a good capture of all the geologies that can have mineralization, of economic mineralization, if you will. Yes, so we developed Africa about 2 months ago. Again, pretty much, like I say, forced out of Canada because of the NRCan's indifference. So we decided to also go after Africa in terms of potential mineable deposits or targets, if you will. So here's a nice desert shot within Egypt. And I want to point out that, again, we have a 3% copper model to the upper left here. And we have chrysocolla. We basically have copper oxides coming out of the satellite image, if you will, to the lower right of this image. So you see a lot of this in desert areas with our classifications. You'll actually, I'll use the classifications just a bird eye down to where I can actually see the oxides coming out of the rock. So it's always lovely to see oxides. It's always lovely to see gaussons associated with the geological machine learning. I see a lot of it. Here's another example. I went to an old British geological society map. It was from 1920s, and you can see the report name, Farquharson. So basically, they went into Somalia way back then, and if you look below here, you can see that they identified lead gold right basically in the center of their old map. On the upper map, that's our geological machine learning map of Africa, and we're looking at our gold being exactly in the same spot as they've identified gold back in the 1920s. So all of us geologists love old maps. We like looking at old maps and comparing the new maps. Old maps are great, and it's lovely to see the geological machine learning corresponding so much with history. The next example, I had basically a position writing for Mining Magazine. So last year, Mining Magazine assigned me to do a review on 5 of the top 10 exploration programs on the planet. So it's a little bit of an ironical situation for me. Here I was writing articles for Mining Magazine as a writer, and well, Mining Magazine, Mining Journal, and they had me review some of the top exploration programs, successes, if you will, across the planet. So F3 uranium, they assigned me to write an article on F3 uranium. But while I was there in Saskatchewan reviewing F3 uranium's uranium oxide deposit, I decided to run basically look at my machine learning map across Saskatchewan. I literally, my company has not trained any algorithms on uranium oxide. So it was a very big surprise to us, but just south of F3 property, they had a 43101 program, definition program, if you will, for 43101 on a uranium oxide deposit just south of F3. And if you look in the middle of the picture, that's drilling done on ice in Saskatchewan for uranium oxide. So they're doing core work along on the river. What was quite unusual and surprising for me was that it turns out that our combination of 10 gram per 10 gold model mixed with nickel had somehow inadvertently identified uranium oxide. And we had to go back and think about it a bit because basically if you look at that little white line on the ice, that's where they're putting the core rigs in along that ice road. Basically what it boils down to is the algorithm had thrown uranium oxide into an unrecognized other category, so it combined gold with nickel to identify uranium oxide. So we had something of a surprise here where we now, it appears, have a uranium oxide map of Saskatchewan. We can also look at properties. We can develop third-party market indices for properties. So for instance, say you have a property, we could work out the areal extent of what the expected high-grade materials would be on that property versus the actual property boundaries. So we don't always have to do a visual thing here because all our results are in vector files. We can compare the property to the distance to roads. We can compare it how much high grade we expect on a property block. So we can actually develop third-party market indices. I know there's some funds out there who love to invest according to non-visual criteria. We can actually achieve that with our geological machine learning. So quick recap. So we can identify missed opportunities for higher grade ore, which you saw in the case of the resource sterilization in Chile. It doesn't matter if you're near or far from a mine, we can go greenfield with the same odds as we have close to a mine. And there's no hindrance there. We're not operating according to how Singer and the mining industry have established themselves to cluster, explore around pre-existing mines. We don't have that hindrance. So we can go far afield, and because we have a surgical approach to exploration as opposed to a wide area surgical approach, if you will. That's a bit of an oxymoron. But we can basically reduce a lot of the road permit work, road development work that goes on with exploration down to a one road, one target exploration approach. And that immediately speeds up things because you're not going into a 9 to 1.5 year road permit exercise every time you have to put in a bigger core rig. So hokey doke, if you guys have any questions.
Thank you, James. If you have a question, please put it in the chat box. We are pretty much at the end of the presentation. So I'm going to say, in a case we don't get to Q&A, close out Q&A, we can always follow up. You can reach out either to James or myself through LinkedIn and get additional information. More than happy to do that.
Or we could share the presentation that I actually built with all the commentary, which doesn't seem to run very well here. We could do that. So
yeah. Well, this is all recorded. It's going to be on the Ahmad YouTube channel. But in addition to that, we'll also include your presentation, which is so well done. I've seen a previous version of it. But in any case, it looks like there are no questions at the moment. We are going to close out. Jane, there's one. What does your fraternity of geologists? Okay.
A good question, right? I've had pitchforks thrown at me, everything from that to when they do give me a chance to explain. One thing I noticed as I've grown older, and I started off in gold exploration. So when you're a young lad, you love going across the countryside, going up hill and dale, exploring everywhere. But what I've done is I've created a process as quickly as possible, finding something that potentially could be developed up to a mine. And I keep saying to folks, well, don't you want to work at a mine? Don't you want to develop a family at a mine? Like you basically can go to a mine, you work, you're going to the same spot all the time, basically. As a geologist, you're doing grade control, when you're young, and I've done it. You're climbing those cliffs, you're going up those mountains, you're going down those creeks, looking in the creek, and we're not really in that age anymore, except for some of the situations I pointed out, like Busang, you're in the depths of a jungle somewhere, being bitten by snakes. But there's been a varied response from geologists, but I do point out that even with drillers, so drillers, there's lots of exploration drillers out there, and then I just point out, well, don't you go from being an exploration driller to being a driller on a site where you can you're drilling for blasting, basically, or you're doing a 43 101 much quicker, which is a much more defined, more reasonable point of work from the perspective of now if you have a family life,
So what's the maximum depth you can go with your algorithm?
Okay, so the surface data mining, it looks like it goes down to about 150 meters, but the gravity data mining, it's just crazy depths, 9.5 kilometers depth.
Okay, is there any other question? I'll give it another 3 seconds. 1, 2, 3. I guess we can close out. thank you all for joining us today. James, this is, as always, very insightful and very exciting. Thank you for taking your time and spending this afternoon and probably a couple of hours, more than a couple of hours in preparation of this presentation. It's highly appreciated. We really want to bring this mining industry into next age so that geologists can be just like rest of us.
Well, I'm hopeful that we can do that because we go from being kind of a friction-filled industry, if you will, from society to being, more surgical. I think that's really what we're trying to achieve here.
Yeah, many, many, many benefits. Thank you all. I'm going to say.
And thank you very much, Nermina, for the opportunity. I very much appreciate it.
I always learn something. Till soon again. Bye for now.
Okay, take care.